All right, we're ready for our move on to Chapter 19. Now, Chapter 19 is all about reaction rates. Now, it's just like when you're in elementary school, you get on the old merry-go-round and you have somebody push you, okay? By how good the pusher is and in which direction they push, that kind of determines on how much fun you have. So in chemistry, by what we have, and how hard it pushes and in which direction it pushes, that's going to determine how fast our reactions go. So the big guy that kind of talks about reaction directions and which way they went was a gentleman by the name of Chatelier. Now he's got his own principle. I don't know, you got to be pretty cool to get your own principle. So Chatelier, he's got his own principle, and it's basically talking about which way reactions will move. Now, it's not just any type of reactions, but it's reactions that are at equilibrium. And not just any type of equilibrium, but it's going to be dynamic equilibrium. So first off, we need to talk about what dynamic is versus static. If you're doing static equilibrium or static anything, static is at rest. There's no change going on whatsoever. So if you wanted to bend over and do some toe touches, and you just bend over and don't move at all, that's static. Now if you wanted to get a really good stretch, you do a dynamic stretch. That's where your body is moving as well. So if you want to do dynamic toe touches, you would bend over, and then as you're down, you might really get a good stretch that way by moving. Okay, you're still in the overall direction, but now we're moving a little bit more. Okay, it's not just in one stuck position. Okay, so what we're going to talk about is dynamic equilibrium, and Le Chatelier, that's what he described, was things that are at dynamic equilibrium. So let's go ahead and draw a quick little equation. Okay, we're just going to go simple. We're going to go letters. So we've got reaction A plus B. Now, before, we've been drawing just one arrow. Okay, it yields, it makes something. Now, there were dynamic equilibrium, so it's not just going to go in one direction. It's going to come back the other direction too. So we're going to redraw our arrow. It's going to be a little bit different. Okay, so we have an arrow in one direction and one coming back that way. Now, typically, if we get real fancy, if it's pushing in one direction a lot more than the other, we'll draw it longer than the other arrow. But don't worry about that right now. Okay, so reaction A plus B is going to yield product, in this case, C plus D. Now, we can have one thing on this side and two things over here, 3, 4, whatever. Just realize that we just have a reaction taking place here. Now, by doing things to these, we can determine, or we can observe changes. Okay. Now, what we want to do is we want to add a stress. Okay. When you add stress to your life, hopefully you change. If you don't change for the good, obviously it's going to be terrible. But it doesn't really matter to them. They don't know what's good, what's bad, but they're going to change when a stress is added to their body or to their being. Okay. So our stresses that we're going to talk about are going to be concentration. Okay. We just talked about concentration last chapter. Things in molarity. So anytime I draw brackets, I'm going to talk about concentration. So if we're use this right here, and you see a number in there, we're talking about our concentration. Concentration may be going up, concentration may be going down. Okay, so that's one thing we'll be looking for. The other stress that we're going to apply is going to be temperature. Okay, if we add heat, if we take away heat, the temperature is going to be very, very beneficial to us for figuring those things out. Here in a little bit. It'll be a stress. And then the last one's going to be volume. Sorry, the camera died on me if there's a gap in that. So the last one's volume. So all of these are stresses. Now, volume, why would that be a stress? If I push down on something and put it into a smaller size container, obviously something's getting stressed to be put in there. So we'll explain how that's going to go on here in just a second. So let's go ahead and start with concentration. So I'm going to get rid of these, and let's talk about concentration specifically right now. Okay, so if I have a certain amount of A, a certain amount of B, who cares what numbers those are yet? We'll deal with those when we deal with problems. But if I add more A to this, okay, so A is coming in to this solution. Okay, I'm adding more A to my reaction. Which way is the reaction going to go? Is it going to go making more product, or is it going to come back and make more of the reactant? Now, let's think about this. If I'm adding more A, is the reaction going to want to come back the other direction, back to the product side or the reactant side, and make even more A? That just doesn't make any sense. We want to get from this side, hey, you added more A, it stressed me out, I want to move over to the other side. Okay, so that was the Chatelier's principles about concentration. He said if I add more of one thing on one side, it's going to push to the other side. Now, the same can be said if I get rid of A. Okay, so if I remove some A from this, which way is it going to go? Oh, I don't have enough A now. So let's go ahead and make more of the A to make it balanced once more. So that's some things we can do to get things balanced. We can either add or remove. So those are going to be the big key terms we're looking for, is you're either adding something or removing. And that's for concentration. We'll look at actual numbers in class. Okay, so that was concentration. Let's look at temperature. Now, when we covered exothermic, endothermic reactions in our thermochemistry unit, we always talked about the energy units. And we talked about it as actually being a product. So let's say in this case it's C plus D plus, let's go 25 kilojoules. Okay, so that's an actual product, that's an actual thing. Now that is heat energy. Things you're going to see now are we removed heat. Okay, so if I see or I hear the term I removed heat, where's the heat being removed from? Well, the only one that has the heat is this side. So if I remove heat, it's just like me taking A out of the equation earlier. So I remove heat from this. In which way is it going to want to go? Oh, I want to make more heat because I took it out. Okay, so in this case, we're moving in that direction. Now, what would happen if I added heat to the equation? If I add heat, where's my heat at? It's right here. This is now going into it. Do I want more heat? No, I don't want heat. I already have heat. So if I add heat in this case, it's saying let's not make more heat by going in the right direction. Let's go back the other way where I can get rid of some of that heat. Now I know heat sounds really confusing, but if you view it simply as a product, just like we did with concentration, it's going to be much easier on you, I promise. Okay, the last one we're going to cover is going to be volume. Now, volume is only going to apply for gases. So everybody out there paying attention here. Gases. Anything that's not a gas, we don't worry about the volume. So, now it's very important that we look here and we see what these things are. So let's say that this is my gas for A, and let's say B is a liquid, C is a gas, and let's say D is a gas. Okay? Now, it's also very important that we look at the coefficients. So let's say A has a 2, B has a 1, C has a 3, and D has a 1 as well. Okay, I don't know why I wrote the 1, so I'm going to get rid of that, and we're good to go. Okay. Now, we know at STP, standard temperature and pressure, that gases occupy a volume of 22.4 liters. Okay, that's important. Brody, you getting this? 22.4 liters, gases only. So, I have a gas right here. Okay, 1 mole occupies 22.4. How many do I have? I've got 2. So on this side, I occupy 44.8 liters of space, just in gas only. Okay, so here's a mole. So that's 2 moles. All right, this side, over here. Both of them are gases. So I have 3 plus 1, which is 4 moles. So it's going to be twice as big as this side, or 89.6 liters. So if I'm on this side, let me write that a little bit different. If I'm on the reactant side, or the product side, I am now occupying an area like this, okay, much bigger. So this is quite a bit bigger than this one. if I apply pressure to the system, is it going to want to be big, or is the pressure going to want to push it small? Pressure wants to push it small. So if I push down on it, it's not going to want to stay big. The stress here is going to cause it to say, it's a lot of work to stay big. I want to get small. So it's going to push down to where it gets smaller and smaller. Okay? So in this case, if I add pressure to this system, to this reaction, I'm going to make it smaller. Okay? So the stress here causes it to get smaller. Now what if I removed pressure? Okay, if I remove pressure, it's now going to want to expand out. It's like that big old Thanksgiving dinner. You know, you unbutton that buckle on your pants, or you undo your belt. Now you got more room to expand outwards. Okay, that's not a good thing. Don't do that. But we have the room, so now it's easier for it to expand. So reducing pressure is going to move towards the bigger one. Now, what would happen if both of the moles are the same? Okay, let's say I have 4 moles on both sides. If I have 4 moles on both sides, it's going to be a wash. Okay? Absolutely nothing's going to happen. Who cares? Okay? The pressure is not going to cause any stress one direction or another, so we're okay. All right, so that's Le Chatelier's principle. Like I said, if you get the basics, you know concentration, you know, what was the other thing I was talking about? Volume, and you know heat, temperature. Then you at least have the basics down for that. You'll be able to start some problems. We'll be able to see some things actually taking place. All right, have a great evening. We'll see you tomorrow.